Welcome back everyone to part 3. In the previous section, we discussed this time series generator object in detail, and we also discussed that we can specify our own number of inputs as well as our own number of features. What we're going to do now is we're actually going to create the model and then fit it to that generator object. We'll say from keras.models import sequential, from keras.layers import dense for our final output layer, and then we'll say from keras.layers import LSTM. That's the long short-term memory unit. Now basically this is actually going to be a very simple model. We'll say model is equal to sequential, and then we're going to add in an LSTM layer, and then we're going to add in quite a few neurons to this LSTM layer. I'm going to put in 150. Keep in mind this is something you can edit. It can be smaller or larger, and there's really only kind of one true way to find out here, and that's to play around with the number of long short-term memory neurons you use and then see which ones perform better. It's really going to depend on your data, how complex it is, if it has seasonality or not. So there's not really a good answer I can give you here as far as what number of neurons you should use for this LSTM layer. But a good starting point would probably be 100 neurons, and then see if increasing the neurons after that affects your performance. So we're going to say LSTM there for 150 neurons. We'll go ahead and say the activation function is a rectified linear unit. And then the last thing we want to specify is the input shape. And we'll specify that the input shape is just equal to n input, which remember we defined above, and then n features. So what that actually means is, recall back when we were saying the time series generator object, we could decide on n input, which decides how much you actually see before the y label, so 3 time steps ahead, 1 time step ahead, etc. And then number of features. For a time series, this is essentially always going to be 1 because you only have the kind of one singular timestamp as your single feature. So that's why we'll say n features, keep it at 1, and input, that's something you can play around with. So I'm going to copy and paste this cell to be kind of right below here. And this is something we're going to play around with later. So we have our time series generator object. Right now it's just on the training data. So we'll go ahead and rename this train generator. Next, what we're going to do is we'll go ahead and change n input to be 12. That way we go ahead and look at a full year's worth of data, or 12 months, before predicting the 13th month. And n features is going to be staying at 1, and we'll use it later on, but basically all n features defines is how many columns you have, and we really just have one column of data, which is the timestamp for the y. Okay, so we have sequential, and we have our LSTM 150 neurons. After this, we just essentially need to aggregate all those neurons to a single prediction. So we'll say model add, and then we'll add in a singular dense neuron, which will then directly output our prediction. And after this, we will compile it. We'll say the optimizer here is equal to an atom optimizer, and that loss is equal to mean squared error. Okay, so we have our sequential model ready to go, and we have our training generator. In order to check out the summary of the model, simply say model.summary, and you should see something that looks like this. Again, you may want to play around with the number of neurons in the LSTM layer, and what we're going to do is now we're going to fit it to our training generator. And to do that, we simply say model.fitGenerator, and then we pass in that training generator, and then you decide on the number of epochs to train for. Again, the more epochs you use, the longer it's going to take to train. 1 epoch is just a single entire run through all of your training data. So we'll go ahead and say 25 epochs. You can experiment with this. Go ahead and run that. And this is going to take some time. It'll take a few seconds per epoch on a really fast computer. So I have a very fast computer, and it takes me around somewhere between 1 to 10 seconds per epoch. So I'll go ahead and fast forward in time until this is done training on those 25 epochs. Essentially 25 full runs through the training data. Alright, so fast forward in time, this is now trained for 25 epochs, and basically you can see here that after a certain number of epochs, you should see this loss eventually start to converge around a single value. If the loss is still continually going down, you may want to retrain for a couple more epochs. But for our data set, somewhere over or around 25, you should be able to get some sort of convergence around this loss value. So what we're going to do is I'm going to go ahead and plot out, just as we did before, our loss. So we can say model.history.history.keys, and recall off of this dictionary, there's a loss value. So what I can do is I can simply say plt.plot for the range in the length of model.history.history loss. And this is something we already did in Keras Basics. And then making sure my parentheses match up here. Then I will plot this out against model.history.history loss. Okay, so here we can see the plot of our loss. And if this is a little confusing for you, you can simply just take this out and say my loss, and then you can just pass that in instead. You can say my loss here versus my loss there. So that's the exact same thing, and that's the thing we did in the Keras Basics notebook. So you can see here, we get significant reduction over the first couple of epochs, and then probably somewhere even around like 15, we start to see convergence. Okay, so now how do we actually evaluate this on the test data? So what we need to do is we first need to create an evaluation batch. Recall that our network basically trains one time step ahead. So right now, our network will see 12 history steps and then predict step 13. So what we need to do is to start off, we need the last 12 points of the training data in order to predict point 1 of the test data. And then we'll continue that cycle, gradually grabbing less from the training data and then just forecasting into the test data point. So let's go ahead and say our first evaluation batch is equal to scale to train. The important thing to note is our network can only run on scaled data because it was trained on scaled data. And then we'll say -12 all the way to the end. So if we take a look at our first evaluation batch, these are the last 12 points of the training set. So recall that when we were taking a look at the time series generator object right here, when we actually asked for the shape of the arrays that were being returned, it was three-dimensional. So what we need to do is we need to reshape this first evaluation batch because this shape is not the shape that the network expects it in. Instead, what we're going to do is we'll say first evaluation batch, and then we're going to reshape this, and it's going to be just a single batch. So we pass in a tuple here of 1, comma, and then it's by n input and n features, essentially 12 by 1. So go ahead and run that. And if you get an error at this point, it means you've done something wrong or committed some typo before. So essentially go back and run our notebook. But here's our first evaluation batch reshaped. Notice it pretty much looks exactly the same, except now there's 3 brackets there at the top. So what I'm going to do is just reassign this so it keeps that reshaping. And then what I'm going to do is call my model, and I will say predict on that first evaluation batch. And then it spits out this array prediction. So what does that actually mean? That means that given these 12 points, since it's designed to take in 12 points and predict a 13th point outside of that set, that given those last points of the training data, it predicts that this should be the first point of the test data set. Okay, so notice again here that this value kind of has strange dimensions. So it's an array holding these 2 brackets together. So what we're going to do is we'll later see how we can reshape this in order to plot it out. But first what we want to do is we want to be able to not just predict the first point in the test set, but the entire test set. In fact, this is essentially going to show you how to forecast into the future. So now let's go ahead and show you how to forecast using this RNN model that we just trained. So in order to do this, I'm first going to create an empty placeholder for test predictions. And then I will say that my first evaluation batch, so we'll say my first evaluation batch is equal to my scaled training data. And just to kind of make this a little more generic, I will say minus n underscore input all the way to the end. That way, if you edit the input length from before, so remember all the way up here, we defined, okay, input 12, predict 1 into the future. If you decide to play around with that value, then using this code, minus n input, is the more generalized version of what we did up here, which was minus 12. Okay, so our first evaluation batch coming straight from the training data, and then we'll say our current batch is equal to that same first evaluation batch, and we're just going to reshape it as we did before. So then go ahead and copy this reshape code, because that's the format that this time series generator created for us. So what's actually going on here? This is going to be a kind of holding my predictions as we go along. And in fact, I'll put these comments above. This is probably the most complex part of this entire project, is just how do we actually forecast using this. And it's basically just making sure that our NumPy arrays are the correct dimensions. So here's the first evaluation patch. Essentially, the last n input points from the training set. And then we're using this in order to predict kind of 1 point into the future. Essentially, on the first round, it'll be the first point in the test set. So essentially, if I run scaled test, notice the first point should be around kind of 0.6 or 0.82, and we predict 0.8. So we're a little off, but kind of getting there. So holding my predictions, last n inputs, just as we did. And what we want to do is we want to essentially cycle through this and then add on more of our predictions. So we're going to say here is for I in range length of my test set, we'll do the following. We'll say that my current prediction is equal to model.predict and predict off the current batch, which remember, the first current batch is essentially going to look like this first evaluation batch. Okay, so what I'm going to do is I only want the prediction value. So if I take a look here, when I said model.predict, it kind of gives me this weird formatting. So I'm going to, if I call index off of that, just 0, then it reformats it to not be two-dimensional. So I'm going to be using that in order to get rid of one set of brackets. So off this predict, I'm going to call 0 there in order to get it into some nice formatting. And then that's my current predictions. So let's store that prediction. We'll say test predictions dot append. Make sure I spell append right. Append my current prediction. And then what we're going to do is we're going to update our batch. We'll say my current batch is equal to, and this is probably the most complex part about the dimensions, but we're going to say np append. Notice this is numpy append. We're going to take the current batch and then say colon, 1 colon, comma, colon. And then we're going to append in double braces or double brackets the current prediction along axis is equal to 1. Okay, so this is by far kind of the most complex part of everything that's going on here. So this is actually all the code we need in order to forecast into the future. We're right now only forecasting into the test length of the future, but we can always expand on this to forecast further beyond the test. But let's first kind of go line by line, and then we'll focus a lot on this last line. And it's actually not too bad when you kind of simplify it down to what it's actually doing. But first off, I want to later plot my predictions. So I have this empty list that's going to hold my predictions. That's step 1. Then step 2 is to grab the first evaluation batch. And why are we doing this again? Well, recall that our model takes in 12 historical points and then outputs a 13th point, which means if I want to try to predict that very first point in the test set, I'm going to need the 12 historical values right behind it, which are going to be the last 12 values of my training set. So that's what I'm doing here. I'm grabbing the last n number of input values from my training set. And then here I simply reshape this to the format the RNN wants, which is the same format as the time series generator outputs. So that's where I got this particular shape values. Time series generator outputs essentially batch dimensions, comma, n underscore input dimensions, comma, n features. Okay, so right now it's kind of all generalized. And so that's my current batch. Those are my first batches of historical training values in order to predict the 13th value. So when we start off, this current batch is going to be equal to those last 12 points of the training set. Now, this is where I decide how far into the future will I forecast. And right now, it's just going to the length of the test set. But you can always swap this out to be however many points in the future you want to predict. If you want to predict 24 points into the future, simply replace length of test with 24. And so what happens is you'll predict the 12 of the test and then a further 12. That's assuming you don't retrain your model on the entirety of the data set, which you should probably do. But right now we're just kind of doing the evaluation part. Okay, so I'm going to forecast the length of the test set into the future for 12 points. So what do? Well, the first thing is I grab my current prediction. So this is essentially one time step ahead of the last 12 points. So one time step ahead of historical 12 points. And that's just passing in that current batch and then predicting off of it. And again, this 0 here is for formatting. So there's my current prediction. And then what I'm going to do is I'll go ahead and store that prediction. Okay, and then what we have to do is, and this is the big part, update the current batch to include the prediction. Okay, so I'm going to go ahead and show you kind of manually what's going on here in this one line. If you're pretty good at NumPy and you kind of already just right off the bat understand what I'm doing here with this kind of a little bit of complex piece of code, you can go ahead and kind of skip forward through the video. But right now, I want to take the time to clearly explain what's going on in this last line, because it's probably the most vital line out of all these, and it's the most complex out of all of them. I'm going to just grab these first 3 lines and put them in a separate cell. Okay, so holding my test predictions, grab that first evaluation batch, which is the last n number of input points from our training data, and then I reshape it to have my current batch, which means I should be able to call model.predict and then pass in my current batch, and it outputs my prediction, just as we did in this line here. So then, if I say 0, I get this nice little single array. So all that does is, if you comment it out, it gets rid of those double brackets. Okay, so I'm going to label this as my first prediction. So here's my first prediction value. It's right here. And then if I take a look at my current batch, it's right here, these 12 historical points. What I want to do now is I want to forecast one time step ahead further than 0.8. But recall, I need 12 historical values. So what am I going to do? Well, what I'm going to do is I'm going to drop the first value from the current batch and then add on my prediction to the very end. So right now, if I check out my current batch shape, it's 1, 12, 1. So what I'm going to do is use this piece of code in order to kind of tack on this first prediction and then get rid of the first item. So that's where this line of code comes into play. So again, take a look at the shape. It's 1 by 12 by 1. And if I say current batch, colon, it means everything from this dimension. 1 colon means starting from index 1, go ahead and grab all the way to the end. And then colon here says everything in this dimension. So essentially what that does is, whoops, that meant to be a comment. If I check out my current batch and I were to apply this sort of slice notation on it, it's the exact same thing in the exact same dimensions, except for this very first point of 0.63. This indexing just gets rid of that point. So then if I take a look at the shape here, it's only 1, 11, 1. Then what I'm going to do is I'm going to add on this first prediction. So how do I do that? I simply do that with np.append. I take that current batch of now these 11 points right here, dropping that first one, and then I tack on that current prediction. And the way we're going to do that, in order to make sure dimensions keep the same, notice there's 2 square brackets here inside of the most outer square bracket, which means I need to say 2 square brackets and then pass in my case, my first prediction. And then finally, I specify that it should go along axis equal to 1, because if I take a look at, again, the shape here, notice that axis equal to 1, that's the one I want to add on to. So my current batch, I'm going to grab those 11 values and then tack on my first prediction. And so when I see this on my current batch, I get back those first 11 values that are historical and then add on my prediction. So if I take a look at the original current batch, I can make the direct comparison. Notice this one starts at 0.63 and ends at 0.55. This one starts off at 0.8, which is what we had here as the second value, and then ends not just with 0.55, but then with the added prediction. And now these are going to be the next 12 historical points, and I forecast my next one on that. And I keep repeating this process, and eventually the recurrent neural network is going to, if you go long enough, do forecasts on forecasts. So that's just the way the neural network is going to work. Through some underlying model, it takes the 12 historical points, outputs the 13th point, and if you keep forecasting as you kind of go along step by step, eventually you'll have 12 fully generated points from the model and then forecast 1 extra point. So as you can imagine, eventually as you forecast super far into the future, you're kind of forecasting on further estimations. So eventually it'll probably get very noisy if you were to try to forecast, 10 years into the future. So those are some of the limitations of the recurrent neural network because of the specific way the model was trained to use 12 historical points and then do 1 into the future. Okay, so that is what is going on through this entire cell. So I'm going to copy everything in this cell and just scroll down here. We'll go ahead and run that. And we're doing this for the length of the test set. So I run that, and now I have my test predictions. So if I see test predictions, here are my predictions on the test set. Now something to note here is they're all still scaled, and I probably want to invert that scaling process. So the way we do that is quite simple. We simply say true predictions is equal to, we call our scalar object, and then we call inverse transform on those test predictions. Run that. And now if I take a look at my true predictions, I have my true predicted values. So if I take a look at my test set, I have right now just the sales column. What I'm going to do off that test set, I'll also add in predictions and set that equal to the true predictions I just made. So now I have this nice data frame with not only my sales, but also the predictions, which means I can plot them out. We can say something like fig size equal to 12 by 8, and I don't even need to worry about legends or labels since this is all now in the same data frame. I can see my sales versus my predicted values. Now keep in mind, there is a little bit of randomness when you're training your recurrent neural network, and you may not get the exact values I get here, but more or less, there should be some sort of lining up to these peaks and valleys. You can see here that our predictions aren't super great here, which may indicate that we need to train for more epochs, and depending on what kind of computer you're running or how many epochs you trained for, recall that there is kind of a random start to a lot of these optimization processes that the neural network does. So your results may not be exactly like mine, specifically because we also didn't set any sort of seed anywhere. So just keep that in mind that if you get slightly different results, then that's totally okay. Now, if you get results that are way off, maybe you get like a flat line around 0 as your predictions, then you probably made a mistake somewhere and you should try running our notebook. Okay, so after you've run this model, you probably want to save all your kind of hard-earned training. And that's actually quite easy. To do that, we simply say model.save, and then you save this as whatever you want. So you can say my cool model.h5 is the extension here. And now that model has been saved into whatever directory you're in. So if you type pwd, this will kind of report back the entire directory of where this .h5 model was. And if you want to ever load that model in a new notebook, you simply say from keras.models, import load model, and you can say my new model is equal to, and then you call that load model functionality, and then whatever the name of your model was. And you can also pass in the full file path if you're located somewhere else on your computer. And that sometimes takes a little bit of time to load the weights, but after doing that, you should be able to kind of see a summary of the model here, and it should match up with what we had before. And this new model can then perform predictions just like the old model up here. And last, to end this, sometimes students ask a lot of questions on, okay, I saw how you evaluated on the test set, but how do I forecast into the true unknown future? Well, keep in mind, that's actually the exact same process we did here. You simply expand the length of what you're forecasting to. So right now we only train on the training data, assuming that you don't want to go back and retrain on all the data, so you didn't really want those last 12 points, you simply just expand the range here. So I could say something like 50 points. Run that, and then my test predictions are now 50 points into the future here. And recall, as you go further and further, you're likely to get more and more noise since you're predicting off of predictions. And then you can do the inverse of these predictions to get back your true predictions. And something to keep in mind that at that point, you wouldn't really be able to run this line of adding it onto your current existing data frame because true predictions, the length of it doesn't match up with your test set. So just keep that in mind. You'll have to kind of manually yourself reorganize this data, but using what you already know about pandas and time series indices, you should be able to easily do that. And in fact, we've done things like this already several times throughout the course. So just adding on values to new timestamp information. But that's the basic idea here. Essentially, you would just go back, retrain on all your data, and then update this range to whatever you want, because that's the exact same process. Previously, we just limited it to the test set, but you can go back or into the future as far as you want. Okay, that's it for recurrent neural networks. Coming up next, you'll have an exercise to test your knowledge based off of the project we did here. I'll see you there.